All right, this week we're going to talk about optimization, which is a new word problem for us. It's a pretty important one. It's one you guys will definitely see on the AP test next year. But basically, to optimize something means to find either its minimum value or its maximum value. And together we call those the optimal values. So basically, if you're looking at a word problem and you notice that it says, find the maximum value of this, or find, the largest that this thing reaches, or the smallest, anything about minimizing or maximizing, that's what we call an optimization problem. Now, basically, these are just word problems of the last thing we did. So what we just finished doing in 5.1 was the extreme value theorem, where we found an absolute minimum and or maximum over a closed interval. And that's exactly what we're doing here for this week, but it's going to be a word problem. So what I want to do for today, instead of throwing the whole thing at you at once, which can be kind of confusing, I'm going to focus on just one part. And that part is finding the closed interval, because that can be tricky in a word problem. It's not going to say in the problem on the closed interval 2 to 10. You're going to have to figure out what the closed interval is based on the words. So here's how it's going to work. Once you figure out what the variable is that you're working with, and that, again, that's part 2 lesson, is talking about how to figure out the variables. But once you've done that, to figure out your closed interval, you have to take that variable within the context of the problem and say, what's the absolute smallest this could be? What's the absolute largest this could be? And then that gives you your closed interval. Now, it's not like a formula or anything. It's not like, oh, you plug this number in and the answer gives you the lower bound and you plug this in. You just have to think your way through. You have to read the question and actually like put yourself into the question and say, if I was actually building this thing that we're talking about in the question, or whatever the question is about, what's the smallest this thing could be? What's the biggest this thing could be? That gives you your closed interval. So let's walk through a couple examples together, and you guys, I think we'll see what I mean. So right here on the top is an actual question. That's what an optimization question looks like. Now, we're not actually going to answer the whole question. But what it says is you're making a rectangular enclosure against a building. You have 200 feet of fencing. What is the maximum area of the enclosure that you can build? So we know that it's a optimization problem because it asks for maximum area. Any question that asks for a maximum or a minimum is an optimization question. And basically, to give you a sense of what's happening in the question, we're building like a fenced in area, but we're saying we're building it against some sort of structure, some sort of building. So we don't have to build all 4 walls of the fence. The fence is here, here, and here. We're using the building as one side, and we're building the other 3 sides of the structure. All right, now, like I said, we're not going to answer the question yet. We'll answer questions like this in part 2. But what we're going to do is we're going to focus on just the closed intervals for today. So I said, what is the closed interval that we're working on if x is the variable used? So what I want to do is I want to kind of set up this closed interval here. And I want to say, what is the smallest x can be? And what is the largest x can possibly be? So what I'm talking about for x is just this side of the fence. I'll highlight it in purple right here. That's x. So let's start with the smallest. The smallest that x could be would be 0. I can't put a negative number, and you can't have a fence that's like negative 10 feet long. That doesn't make sense. So we're dealing with only 0 and positives. So then I think to myself, okay, I mean, is there any limit? Does it say in the question that what each side has to be at least 10 feet? If it said that, then yeah, my minimum would be 10. But it doesn't say anything like that. So really what I could do is I could say, let's just make x 0. let's take the whole 200 feet and put it on the other two sides. It wouldn't build a very good enclosure. They would actually be stuck together. But theoretically, it's possible. So the smallest x could be is 0. And then you say, well, what's the largest x could be? And it's kind of the opposite concept. You'd say, what if I forget about the two sides? And I take my entire 200 feet of fence and just put it for x. That would be the largest x could be. Again, it wouldn't make a good enclosure because you'd basically just be sticking 200 feet of fence against the wall and you wouldn't have any area at all. It wouldn't even really be an enclosure. But that's the maximum. You can't do 201 feet because you don't have that much. It says in the question you only have 200 feet. So that's how you create the closed interval for these problems, is you ask yourself in the question, what's the absolute smallest that number can be? And what's the absolute biggest based on what the question is described. So for this question, for that one side there, that x, the smallest it could be is 0, and the biggest it could be is 200. Now after that, I said, okay, well, what if it's y? What if we're actually using y instead of x as our variable? And again, we'll talk in part 2 about when you use x and when you use y. That's not really what we're doing right now. But if we did decide to use y in the problem, then what's our closed interval? Now y is actually, remember, y is two fences. It only says y once in the problem, but if you're building a rectangle, both of these sides on the edges are going to be the same. So this is actually a y over here also. You want to recognize that. So the y is this fence here and this fence here. So you're saying, now if you're looking at each of those fences individually, and you're saying what's the shortest it could be, it's going to be a 0 again. And actually that's a very common lower bound for real life word problems. Not in every single one, but in a lot of these problems, when you're figuring out your closed interval, the lower bound is going to be 0. So then you say, okay, well, what's the biggest y could be? Now, it's not 200. Some people might say, oh, well, it's the same as for both. It's 0 to 200. But see, it can't be, because if I put 200 feet of fence right here, then I have nothing left over for here. And we need to have both fences built. The y represents both fences. So what you do is you actually just divide by 2. The biggest y could be is 100. And again, because if y was 101, then I have two 101 foot fences. Together that adds up to 202 feet. I don't have that much. So what I did is I just kind of thought my way through it. I just looked at the picture and I said, okay, based on that picture and based on the fact that I have 200 feet of fence for this project, what's the biggest x could be? What's the biggest y could be? So if my variable was x, my closed interval for this problem would be 0 to 200. And if my variable was y, it would be 0 to 100. And basically in part 2, we'll actually answer this question. There are ones like it, maybe not this exact one, but we'll answer questions like this. And when you get to the part where you're going to use the extreme value theorem, that's your closed interval. So those are the endpoints that you test in that problem. Let's do one more, because this is an interesting question. It's less of a real life question, more conceptual. But it says, which point or points on the graph of y equals x squared are closest to the point 0, 2. Now, before we worry about closed intervals, I'm going to draw a picture of that. So right here, y equals x squared is just this basic parabola right here. And let's say that the point 0, 2, that would be just up 2. So let's say that's 1, 2. We'll put it right here. Say the point 0, 2 is right here. So we're saying which point or points on the graph are closest to that blue point right there. Now what you want to realize, what we're actually doing, like, let me just pick a point randomly on the graph. Let's say I pick this point right here, and I call it x comma y. And let's say I measure the distance in between them. I'll call it d for distance. Now, what I'm actually asking you guys to do in this question is to minimize the distance. So it is an optimization problem. This is one where I was saying it can be a little bit tricky. It doesn't say anywhere in the question, minimize this or maximize that. It says which points are the closest. So you'll have to read that and recognize that you're trying to minimize distance, and it is an optimization question. All right, so let's answer each question. Let's start with x. I said, what is the closed interval if x is the variable used? Well, x in this problem is just the x value of the point on the graph. So if you say in this question, what's my closed interval? What's the biggest or smallest x can be? Well, there actually isn't one for this problem, and that's why I put this one on there. I just wanted you to recognize that not every question has a closed interval. X in this problem can be any number, because all we're talking about is the graph of y equals x squared. So I can plug any number I want in for x. The domain is unlimited. Basically that's what these arrows on the end mean. An arrow kind of going up and to the right or left means forever in that direction. So basically for x, for my closed interval, I would say none, or you could say all real numbers, or you could say the open interval from negative infinity to infinity. It means when you get to the part with the extreme value theorem, there are no endpoints to test. You only test critical values for this one. Now let's talk about y. Now y has no upper bound, because if you're talking about y values of this function, again, these same arrows are pointing up. So there's no upper bound for y. It's going to go forever. But it does have a lower bound. The lowest y reaches is 0. The graph never dips below 0. So if y is your variable in this question, you would have a lower bound of 0, but you would not have an upper bound. So I would put infinity like this. And again, when you get to the extreme value theorem part, it means you do have to test 0, because that is an endpoint, but that and the critical values are the only ones. You don't need to test any upper bound for y, because there isn't one. So I threw in this last example just to show you that it's not always a closed interval on both ends every single time. Our first example did work out that way, and it ends up looking exactly like our extreme value theorem question, where maybe our variable was x. So our closed interval was 0 to 200. We test 0, we test 200, we test the critical values. But this one's a little bit different. This one for x has no endpoint, so you only test critical values. And for y, it has one endpoint, but not the other. So you have to test 0 plus any positive critical values. So that's all we're doing for part 1. I just wanted to spend one day having you guys really understand this concept of picking an interval, usually a closed interval, but not always, picking an interval out of a word problem so that when we get to that step, you're ready to do that. And in part 2, we'll actually solve the full problems.